Hello, everyone, and welcome to phyloseminar.org. The current theme is branch-specific diversification inference, by which I mean learning about the diversification process via phylogenetic. If this is macroevolution, then we're talking about speciation and extinction. And if this is microevolution, then we're talking about fitness estimation. Today, we'll hear from Sebastian Höhna on his Bayesian approach for estimating branch-specific speciation and extinction rates. If you want to ask a question, you can either tweet at phyloseminar or type your question in the live chat box to the right of video on YouTube. Sebastian got his master's degree in computer science at the University of Auckland under the supervision of Alexei Drummond. Even though this was only a master's thesis, it started many important lines of research, including ones that we are currently exploring in my group. He then continued his work from Stockholm University under the supervision of Tom Britton and Frederick Ronquist, and then he did Miller postdoc with John Holzenbeck and Rasmus Nielsen. He continued to innovate, leading to a lot of new work on estimation of birth-death processes, and as well as developing RevBayes, a flexible and powerful tool for doing inference under phylogenetic models. Welcome, Sebastian, and thanks for participating.
Yeah, welcome everyone, and thanks Eric for inviting me, giving me the chance here to speak about my research. So today I'm talking a little bit more in general about estimating diversification rates from molecular phylogenies. Which has as the centerpiece, as Eric mentioned in the introduction, estimating branch-specific diversification rates. So for the motivation for this research is that we are basically interested in patterns of diversification in a macroevolutionary scale. And one type of questions that we are interested in asking is, are diversification rates changing on a global scheme for our study group because of diversity dependence or other ecological driving factors? Or are our diversification rates changing through time because of environmental factors? These environmental factors could be paleotemperature, could be also CO2 levels or other climatic factors that affect the entire study group, and because of that, change the rates of speciation and extinction over time. We could be also on a global level be interested in mass extinction events that are affecting the historical biodiversity, where we then have a point event where a lot of biodiversity is lost at a given point in time. We could also be interested in exactly the opposite type of an event where we have speciation bursts. And speciation bursts are, for example, events where there's habitat splitting, for example, islands or river formations, and a lot of speciation events happen actually at the same event or moment of time. Another type of patterns of diversification that we're interested in is key innovations. Key innovations are events that happen along a specific lineage, and due to that key innovation event, that new lineage or that new clade that is forming has a different rate of speciation and extinction. And lastly, the type of research that we're interested in is if there are specific cladogenetic events that have impacts also on changes of the character that we are observing, but also changes on the speciation and extinction events. And the specific type of research that I've been doing, that example we have is, for example, chromosome number evolution, where a change in the number of chromosomes is leading also to a speciation event. So that was the general overview over the type of processes or types of patterns that we are interested in. But I want to backstep now a little bit and start talking about the type of processes and the underlying theory that we're using for estimating these rates. So we're starting with the birth-death process, and the birth-death process always starts with one lineage, or we're assuming that it starts with one lineage at a time. Then there's a speciation event. We have two species that are evolving over time, and there can be more speciation events. After a little bit of time, we gain more diversity, have several species, but then we can also have extinction events. So for example, here we see that we had some speciation events and some extinction events, and for the most part of this talk, we are only assuming that we have the species observed at the present time. So only extant species observed. I'm also switching then back and forth to the types of processes that we are now developing, where we have extinct species in our phylogenies as well. So under this process, when we look at the little bit more complex form, because the birth-death process is the form that we have been using a lot, if we're extending it, we see at the top part here in the slide that speciation and extinction rates can change through time. And for the mathematical convenience, we're breaking up our time in discrete time intervals. In this example, we're breaking up time in time intervals of 10 million years. And then we say that at every time interval, we have a different speciation and extinction rate. And that rate shift event happen exactly at these given times. Then we can calculate the probability of observing the phylogenetic tree, which we are treating as the data, by calculating the probability of the tree shape, so the tree topology, times the product of all the probabilities of all the speciation events, times the probability of all the segments along the branches of our reconstructed tree. So this is the part that we are seeing in figure C at the bottom, where we are saying a branch segment is a segment where the speciation and extinction rates are the same. So we only need to find the equations how we can calculate that speciation and extinction rate. So under the standard birth-death process to derive these probability equations, we can say that we have on an observed lineage, there could be either no speciation event, there could be a speciation event and the left lineage went extinct, or there could be a speciation event and the right lineage went extinct. The other part that we also need to calculate that probability, because I was just mentioning that there's a chance that one lineage goes extinct, we also need to calculate then what is the actual probability that the lineage goes extinct. And a lineage can go extinct under the birth-death process in 3 different kind of scenarios. The first scenario is that the lineage goes extinct in a tiny time interval. The second scenario is that in a really small time interval, there was no event, but then later, before the present, the lineage went extinct. The last example is that there could have been a speciation event, and then both descendant lineages must go extinct before the present. And this can be, once we have just listed down all these different types of scenarios, we can actually write down what the differential equation is. This is what we see as the example there, that each part that corresponds to one of the scenarios that I've listed here for the extinction probabilities corresponds to actually one of these terms for calculating what the probability of extinction is. Once we have listed that, we can solve the numerical. We can solve the differential equations or reformat it so that we write it in a standard form.
Sorry, Sebastian, can you just go through that middle equation, number 2 again?
The middle equation is we have, so there's, in the middle part, we have no speciation event, we have also no extinction event. So it's 1 minus the probability that there's extinction, minus the probability that there was a speciation event, time that is the probability that the lineage goes extinct later on, but before the present.
Okay, I see. That's what that E term means. Got it.
Yes. So this is not quite the usual way how we would look at the standard constant rate birth-death process, but I've chosen to start explaining it in this way because all of this and these other processes that I'm going to talk about today will be extensions. So I try to use the exact same format in deriving these probabilities and showing how they differ and how they're similar to this standard birth-death process. So to come back to the slide, how we're actually calculating the probabilities for the branch-specific, for the episodic birth-death process, is that we can actually solve these differential equations analytically. And I've presented here just what these analytical solutions are. It's not really important that most practitioners know what these analytical solutions are, but it's kind of neat to see that there are, for these types of processes, there are analytical solutions available that we can just plug into a computer program to solve and calculate what the probability of the observed phylogenetic tree that we have from our molecular analyses. So one of the examples that I've been involved in was looking at these Apollo butterflies. And on the left side, we see the molecular phylogenies of these butterflies. And at the bottom of that figure, we can also see what the paleontological timescale is, how a little bit the high Tibetan plateau has changed over this time. And on the right-hand side, we see two different R packages that we use for estimating how the diversification rates have changed over time. And here we really see that there was, in the comet analysis that we did, that there was quite an increase towards the Pliocene, towards the present, in the net diversification rate. So the net diversification rate here is the rate of speciation minus the rate of extinction. We also did in this example, we used three-part package, and we looked in if there's some signal for mass extinction events, and where you could also see that in the mid-Miocene there could actually be a mass extinction event that could have possibly drove that change in the net diversification rates. So once we actually have seen that these speciation and extinction rates are changing through time, we could ask ourselves the question, is that correlated with some environmental factor? And in my line of work, what we are doing, we're trying to build up regression models to see if there's the correlation between the speciation rate or the extinction rate to some environmental factor. So when we have the speciation rate lambda, we say that is built up by a regression function where we have alpha, that is the intercept or the background rate of speciation, plus beta of lambda, which is just the regression slope, and then some environmental variables. So in this little equation that I'm showing here, that could be, for example, CO2, but that could be also environmental temperature or anything else that changes through time. Plus, then there's a little epsilon that is the term for allowing that the speciation rate is also changing independently of my predictor variable. So, for example, it's changing independently of the CO2. And we can set up the same type of regression analysis for our extinction rate. And in this case, we are testing if CO2 is really correlated. So if my beta, my regression slope, is positive and significantly different from 0, then there's a positive correlation. If beta is negative, then there's a negative correlation. And if beta is equal to 0, that means that my speciation and extinction rates are just varying without the environmental variable having any impact on the speciation and extinction rates. So in this analysis, we tested then the paleo temperature and the high Tibetan, or the elevation of the high Tibetan plateau. And we can actually see that the temperature seemed to have some effect, but not as much as the elevation of the high Tibetan plateau, which is what we're seeing at the bottom figure. So at the bottom figure, for example, we see again with the dotted lines what the environmental variable are, and then we see what our estimated speciation and extinction rates are. So I find this is a kind of a very interesting new line of research, but it's quite in the early stages where we need to come up with even better model than this very simple regression model that I just introduced. But anything that we have learned from other statistical approaches can now be included directly into our speciation and extinction analysis. What we can also do is extending that line of work by taking into account also fossils. So if we look at the same process, but now also allowing that we sample fossils through time, is that we again start with one lineage and their speciation event, but now the black circles here represent that there's also fossilization happening along that phylogeny. So then we don't only have the extant taxa sample, but we also have these 3 different fossil samples that we include into our equations. So the nice thing here for this fossilized birth-death process, where we can have also speciation and extinction rates vary through time, we can also find that analytical solution. And if you would go back and compare the slide and the equations that I'm showing to you right now to the one that we have before, the main difference is there that we just added a plus phi term. The phi is the fossilization rate that we're using, and that just appears into a very few places of these solutions, but that is really just the rate that we observed a fossil. So we applied that in a different study that came out a few months ago in systematic biology. And we looked first at estimating speciation and extinction rates from the molecular phylogeny only. And this is what we see on the left-hand side, where we see, for example, that there's some variation in the speciation rate, but basically no variation in the extinction rate. And also very interestingly that the net diversification rate is always positive. And this is because we are observing some taxa at the present time, and the number of taxa at the present time is larger than the number of taxa that we started with. So that means that the net diversification rate must have been positive to reach that number. But if we take the fossils into account and do exactly the same type of analysis, we get much more information because we use more data. So we get a much better picture here for these New World monkeys. And we see that something really more interestingly happened about like 20 million years ago, where there was an increase of the speciation rate. But what I want to point out here again is if we look at the net diversification rate, we see that in the early phase of the New World monkeys, that the net diversification rate was actually negative. So we now, by including these fossils, we can estimate that there was diversity in decline. And then only later on, they bounced back into about like 25 million years ago, the net diversification rate switched to positive. So there should have been an increase in diversity until it now went down again. And quite interestingly, although I'm not quite sure how much we can trust these last time intervals, is that we are seeing that the net diversification rates in the last 2 million years are negative again. And this looks to be that the negative net diversification rate for the last interval is really driven by the extinction rate and not by the speciation rate. So now I'm going to the main part of our latest work, which is the birth-death-shift process. And we call the birth-death-shift process if it's shifting between different diversification rates. So we assume now that the lineage starts in a blue rate category, which is, for example, a slow rate category. Then there's speciation and extinction events. And then there's additional rate shifts event, maybe to a darker blue color, which means that it's a rate category with even higher extinction rates, or it can be switching to the green category when it's higher speciation rates. So the process has now 3 different parameters. It's the speciation rate, the extinction rate, and the rate of shifting towards a new rate category. So this is our birth-death-shift process. So the way how we implemented this birth-death-shift process is looking again at what types of events can happen in a very small time interval. And as I showed before, we can have, for calculating the probability of an observed lineage, we can have that there's no speciation event, no extinction event, and no rate shift event. That is scenario 1. Then we can have scenario 2, where there was actually in a tiny time interval a speciation event, but because we did not observe a speciation event, so the left lineage must have gone extinct. Or it could have been the third scenario where there was the speciation event, and because we didn't observe it, the right lineage must have gone extinct. The fourth type of scenario that we're now including in this new birth-death-shift process is that there can be rate shifts event on the lineages, for example, switching between the blue to the green state or rate categories. And it's also quite important that we are extending our extinction probabilities in the same way. So we're starting with the first scenario that we have, that the lineage could have gone extinct in that small time interval, or it could have been that there was no rate shifts event, no speciation event, and no extinction event, and then there was a subsequent extinction. That was scenario 2. And in scenario 3, we say there could have been a speciation event, and then both lineages go extinct. Or it could have been scenario 4, where there was this rate shift event on that extinct lineage, and then the extinct lineage went extinct under this new, or with these new speciation extinction rates. So how are we actually going to estimate those rates is that we are going to do stochastic character mapping. Because we don't really observe where these types of rate shifts events are happening, we're calculating down on the tree the probabilities of each of the possible diversification rate categories. And then once we have calculated that from the root, we are trying to apply a stochastic, or applying a stochastic character mapping approach by moving forward in very small time intervals and calculating the probability what has happened in this small time interval by then coloring or painting the tree again with the with the randomly chosen rate categories that we are simulating. Okay, so the problem is when we are defining this birth shift process is that ideally we would want to have an infinite number of rate categories, so that we wanted to allow that a new speciation rate after rate shift event is drawn from a prior distribution. But this is numerically impossible, so we can't find any, not even a numerical algorithm, how to solve that. So what we're doing instead is we're doing something similar to what has been used for the standard plus gamma model in phylogenetics, where we have a discrete number of rate categories. So here I was plotting a log normal distribution and show it for 2, 4, 6, 8, 10, or 20 rate categories. And we see the more rate categories that I'm using, the better I'm discretizing or approximating that distribution. So the trick in that is that we then can actually numerically integrate over all the possible rate categories, but the downside is the more rate categories that we're using, the slower the software will be. We performed then a set of analysis estimating on the primate phylogeny, seeing how are the branch-specific speciation rates affected by the choice of the speciation and extinction rates. And in the first panel, or in the first row, we're actually seeing, we're comparing 2 to 4, or 4 to 6, and 6 to 8, and so on, a number of rate categories. So what we're observing here is, for example, in the very last figure, is that if we have 10 or 20 rate categories, there's a very good one-to-one correspondence. So it doesn't really matter if we would have chosen, in this example, 20 rate categories or only 10. Both of them give qualitatively the same results. It looks even here that perhaps 8 rate categories could have been sufficient to approximate that continuous distribution. What we're also looking at the second row is what is our prior on the number of rate shifts. And we're seeing here that actually the prior on the number of rate shifts still has some impact. So we're seeing if we are expecting a priori that there would have been 100 rate shifts versus 50 rate shifts, then we get slightly different branch-specific rate estimates. So to explore a little bit more the behavior of this new birth shift process, we, for example, we implemented our numerical integration routine with the stochastic character mapping, but we also implemented a second approach where we used data augmentation. And now we compared if our implementation works correctly by comparing it to the prior distribution, where the prior distribution, if the number of the rate categories is actually does not have any impact, so that it is Poisson distributed. And on the left figure, we see that our implementation actually gives exactly our prior expectation. On the right-hand side, we're seeing then our prior distribution and the posterior distribution for the estimated number of rate shifts. And we're seeing that under these processes, the number of rate shifts is very biased by the prior that we're choosing. So for example, if we have a prior that is centered on one redshift event, we're also estimating very few redshift events. But if we have a prior that has 20 redshift events, it shifts much more to 20, although you can see that the posterior and the prior are deviating a little bit. So there's a little bit of information, but not much information. So the prior has a much stronger impact compared to the posterior. And this is something that is not just specific to our implementation. This is something that you would expect in these types of models, because there could, a lot of observations could be explained by one large redshift or by several redshifts that are very minor or are in very short time intervals consecutively. So where the impact of having a redshift is not that, not such a large impact. Okay, so that shows that for estimating the number of redshifts, we should always be very concerned about prior sensitivity.
Let's see. So on the left one, you're showing the difference between two different implementations, right?
Right. We are validating our implementation by showing that two different implementations, two different numerical routines, one being based on data augmentation and a different one being based on stochastic character mapping.
Right, but so for the right one, are you saying that basically argues that they both work, and so for the right one, it doesn't matter which one you choose?
Exactly. So since on the left one, we noticed that they're working exactly the same way, which they should be under our expectation because they are exactly the same model. Okay. And on the right one, then we actually only use the stochastic character mapping because that one works computationally much more efficiently. You don't need all the MCMC with reversible-jump MCMC to actually estimate the number of shifts. You just simulate them from the character mappings.
Cool.
Yeah. Okay, so since we're saying the number of redshifts is very difficult to estimate, there's some hope, but not so much information in that. But maybe we are more interested in the end in looking at what is the branch-specific speciation rates. So here we have the same phylogeny and we have basically the same model, only that we varied our prior on the number of estimated shifts. So the first shows when we expect one shift a priori, the second 10, and the last one 20 shifts. And we see that basically we always have one redshift going to the New World monkeys. That's what we identified visually here. But also we could see if we compare what the rates for these branches are to the background rates, that there must have been one redshift. There's a little bit more noise for the other branches, but generally here we are concluding that the branch-specific diversification rate estimates are much more robust to the prior choice than the actual number of the redshifts that we're inferring. So what we also tested and implemented here, what is now specific and new to our stochastic character mapping, is that you can also estimate these hyperparameters. So for example, we applied we used the uniform distribution on the mean speciation rate. So when there's a redshift, you draw a new speciation rate from that prior distribution. And this prior distribution has a mean and a standard deviation. And we applied the prior distribution both on the mean of the speciation rate and the standard deviation of that speciation rate. And interestingly, there is some information in the data to estimate those parameters. So the lighter gray dashed line is the prior distribution, and the solid black line is the posterior distribution that we estimated. Similarly, we can also say we apply a uniform prior distribution between 0 and 100 redshifts. And there's some information, but very widely, that the posterior is saying maybe it's somewhere between 2 and 40 redshifts. So there's, again, not much information in this. And to come back, why this can only be done in our stochastic character mapping is that if we would use data augmentation, we can't estimate these hyperparameters because we are in situations that sometimes we only have one rate category currently drawn from that prior distribution. So we are trying to fit a hyperprior for just one single observation, which makes the MCMC very hard to work. So because there has been quite a lot of the debate in our implementation, and previously we have criticized other implementations such as BAM. So to go back, what is really different in our implementation is that what I highlighted here is that our extinction probability is allowing for rate shifts. You could also, what BAM is doing and what was described in the paper in BAM is that you're not allowing any rate shifts. So basically you're conditioning on that rate shifts must have occurred only on the lineages that are leading to extant species. So the question now is, does that have any impact on my diversification rate estimates? So first we did a little bit, a small simulation study and basing a grid here where this parameter, the little n, the eta parameter, is the rate of shift. So if the rate of shift is 0, then of course there can't have been any rate shift. And we don't see, if we simulate forward in time, here we see the color scheme for how many of our simulations had a rate shift at an extinct lineage. So if there's no rate shift, or the rate of rate shift is 0, it's always 0% of these simulations. If we increase that and we increase the fraction of the relative extinction rate, so for the first one we see actually that we get some simulations that are that have rate shifts at extinct lineage. And if we go further down to the more extreme cases, we're actually seeing that more than 75% of our simulations have rate shifts at extinct lineages. And one part really to note about these simulations is that we had to cut the simulations at a relative extinction rate of 0.6. So where this extinction rate is only 60% of the speciation rate. And the reason for that was if we had a higher relative extinction rate, our simulations were just getting so slow because we're simulating so big trees or so many simulations to actually have observed phylogenies. And you could imagine that there's, for even higher relative extinction rates, the impact of having rate shifts at extinct lineages is even higher. So this is just from the simulation perspective looking at it. But then we also implemented just as an option in RevBayes to look at if we allow rate shifts at extinct lineages. This is our parameter estimates for the same primate phylogeny on the left side, but also if we don't allow it, so if we forbid it, that is on the right-hand side. And you're seeing that here you still get the same general pattern. So the data is, in some cases, like in these cases, overwhelming the information of these modeling assumptions, but you see that they're qualitatively slightly different, like you get slight differences in these parameter estimates, especially if you allow it, you get much clearer the difference between where this rate shift has happened.
Can you say a little intuitively that, like, so the source of the difference, I mean, I understand that you've explained very clearly the difference between the two models, but intuitively what would explain the difference here is that you can have a higher diversification rate that then drops on the extinct lineages? Is that what's going on?
So intuitively it is that if you don't allow rate shifts at extinct lineages, it always means that at this current branch, if there was a speciation event that we didn't observe, that means that new lineage must have gone extinct before the present. And you don't allow it to have any rate shift event. So if the lineage was already in a very fast rate category, the chance of going extinct might be very low. But if you would allow rate shift events, that extinction probability really changes. And this is why, intuitively looking at it, there is really that impact. There's that information from the not observed, the extinct lineages, to what the speciation and extinction rate estimates are. Did that make sense?
Yeah, that does. Yeah, I mean, so you can have a high branch-specific speciation rate, but if it's allowed to go down on extinct lineages, is that right?
Yes. So it's really the information that yeah, if it was already very high, the rate of speciation, but if you allow it to change to a low rate of speciation but a higher rate of extinction, that informs you or gives you more possibility to estimate parameters.
Cool, thanks.
I think I have a double slide in here, so I'll jump over that. What I also did for exactly that same scenario, looking at more interestingly at what are overall these estimates of the speciation, so the mean speciation and extinction rate. And we have always here in blue if we allow for rate shifts at the extinct lineages, and in red if we don't allow them. And generally we see that the speciation and extinction rates that we're estimating are actually slightly different. They're not completely different. In the two different rows I'm showing if I were to use 10 different rate categories or 20 rate categories. I'm basically between those two different settings, approximating that distribution for 10 or 20 rate categories does not have any impact. What is a very interesting result here is if we look at the rate for shifts. So if we allow for rate shifts at extinct lineages, we estimate the rates of shifts to be rather low because there could be all these rate shifts at the extinct lineages. But if we don't allow them, so we're basically conditioning on no rate shift has happened at all the extinct lineages, then we can estimate the shift rate to be extremely high. So this is really pushing it in this analysis to my prior boundary, where I set my maximum for the prior for the shift rate was so that it is 100 rate shifts. So squashing it really to that one side. Which then in the end means that there are some impacts on the speciation and extinction rates itself, if you allow or don't allow the rate shifts at extinct lineages, but even more on the number of rate shifts that you're inferring, because obviously if you're conditioning on a lot of events not happening, that must give you some feedback that if you don't allow them, that you could be very biasing your estimates of how many rate shifts there would have been. Okay, so the example, if we're going now back to the butterfly example, what we have been doing there is we actually compared it in this scenario also to the BAM analysis, and in RevBayes our analysis gives roughly the same estimates, where maybe the exact numbers of the speciation and extinction rates differ, but the problem there is that generally we can't really say that this is always the case. So we found that there was a rate shift really happening at the one major clade leading to it. And once, like similar to estimating diversification rates that are changing through time, where we then might be asking what is correlated to these rate changes. We might be interested here, once we have found that there was a rate shift among these lineages, we try to match it to what sort of key innovation or what characters are correlated to it. And what is very interesting that actually from the modeling perspective, these are our BiSSE and MuSSE models. These type of models had been developed before we actually could estimate the branch-specific rates. And our implementation that we're using in our model actually is using just the extension of the MuSSE model, where we assume that all the character states are unobserved. So here we actually see that the speciation extinction rate shift might be correlated either to the Papaver or the Crassulaceae clade, which is the host plant of these butterflies. So how does this birth-death shift process work when we have observed tip states? This is basically exactly the same process as I was discussing before, except that now we also have, once we have this rate shifts event, we have a specific tip state that we observe. So we have some additional information. So here I'm only drawing the case where we have the binary state, where we have the two different characters like the red one and the blue one, and we have some species observed in the blue state, and we have some species observed in the red state. So this is now, we're not talking about rate shift events anymore, but we're talking about state changes. But it doesn't really matter from our modeling perspective. These are sort of the same thing. It's a state change if you have observed states, or it's a rate change if you don't know what it actually is or what has happened there. So in the binary state speciation and extinction model, how that is working is that we have only two categories. This is if we're looking back to when I started discretizing my distribution, as say, if I would say there's only two categories of my distribution of the speciation rates. And then you can jump between the categories 0 and 1. It's just that in this case, we actually have them observed. And then we have different extinction rates. One of the examples that I've been working on is looking at the invasiveness of the placenta type and checking if that is correlated with the speciation rate. So there's, for placental mammals, there's three different types, or three major types of placenta. There's the epitheliochorial placenta that has the most cell layers. Then there's the endotheliochorial placenta type where you have few cell layers. And then you have the hemichorial placenta type which is the most invasive placenta. So there's the most direct exchange between the mother and the offspring. And the idea behind that is that the offspring, or if there's genetic incompatibility between the mother and the offspring, that both the offspring and the mother is dying. So that speciation should be happening much faster in the hemichorial state. So we set up the model with three different states, three different rate categories, and estimated speciation and extinction rates. And here we're actually seeing that our result shows that the net diversification rate for the hemichorial type, that's the third type in blue, has the actual highest net diversification rate. One of the problems in these types of analysis is that we were saying here we only have three rate categories. And for each of these three rate categories, every change between a placenta type always co-occurs or coincides with a change in the speciation and extinction rate categories. So changes in morphological characters coincide with changes in diversification rate categories. But the problem is what actually happens if there's additional characters, morphological characters that are driving diversification rates, which we didn't see in the study or didn't consider in the study to tease apart these parts. So the solution was proposed by Jeremy Beaulieu and Rainer Mira to look at unobserved hidden characters, to add more characters to see what is the background rate variation, and then look at your focal character to see how much of the rate variation, or is that focal character still associated with rate variation once you have taken into account your background rate variation. And if we were doing that for this placental mammal example, we are seeing that the net diversification rate is a little bit more complex if we allow for a fast and slow background rate variation. But we see that still the hemichorial, so the most invasive placenta type, is correlated with with a higher net diversification rate. But we also see at the last plot on the right side that the background rate A and B, that there's some other characters for placental mammals that has a much bigger effect. So our placenta types might give a very nice and cute story and saying they are actually important for diversification, but probably not the most important one. So that was the extension for the state, and that was the HISSE model that I was just talking about. So for the HISSE model, how we implemented that is we are saying we have the observed character 0 and 1, and we had the category A and B, the fast and slow diversification rate. So now here you can see that now we had 4 categories, while with the placenta types we had in total 6 categories, and you could jump between being fast and slow or between each of the different placenta types. One of the other extensions that we have been working on these models, because so far we have been assuming that all these rate changes or these character changes, these state changes, always happens only anagenetically. But what if there's some of these changes actually happen cladogenetically? For example, in biogeography, that is very commonly the case. And here's just a short example of all the possible changes that we looked at for our chromosome number evolution model, where we're saying that at a cladogenetic event, either no state change, so no chromosome number is changing, or you could actually lose a chromosome, or you could gain a chromosome, or there could be a whole genome duplication, so the number of chromosomes is doubling. And the idea or the motivation behind that is saying if the number of chromosomes is actually changing and only as part of the population, that is really leading to genetic incompatibility, and that's why this should be leading to cladogenetics or to speciation events. And we applied that to quite a set of different phylogenies, and for the Australochia, we see that there's most of these changes happen anagenetically. Only the one little change where we pointed the arrow at is a cladogenetic change. But if we were looking at Carex, we saw that most of these changes were happening cladogenetically, so there were quite a lot of cladogenetic changes compared to the anagenetic changes, which is very interesting to see that there are sometimes the same type of mechanism, like the number of chromosome evolution is driving changes, so where change is always leading to speciation events, and in other groups, these changes are not leading to speciation or extinct, just to speciation events. So that's very data set or study system dependent. The follow-up paper, what we did there is looking at a different system, and we're looking at self-compatibility versus self-incompatibility. And this is, again, tying it up with our stochastic character mapping, because here we were having the observed tip states, and we have 4 different rate categories. And we can actually map exactly where, or we were trying to map exactly where these diversification rate categories have happened. And once we have calculated the most probable character state and diversification rate category on the branches that we are seeing on this phylogeny, then we can see what rate changes there are and from which to which other character change they have been happening. So the motivation behind that study is self-incompatibility at that end. And again, we were setting that up as this type of HISI model. And what we are finding is actually that self-incompatibility, which is shown there in these purple colors. So the self-compatibility is shown in the green colors. So if you're in the fast state, it can actually be a short-term evolutionary advantage. But then once you're in the fast state, we showed that you're always going from that state to the slower state. So in the long term, it's an evolutionary dead end. And here on that side, we're also showing what's the expected waiting time when we map the character, how long it takes to go to that evolutionary dead end. And one of these examples for those groups that we see is that, for example, Clark here first went into the self-compatible state and had that evolutionary advantage, so they diversified. But now all of them went or have been in the self-compatible state for so long that they're in an evolutionary dead end and are in an evolutionary decline. Again, seeing that by that the net diversification rate is estimated to be smaller than 0. So they must be going down in the next millions of years. Okay, similar to what I did before, looking at the example, what we can actually do if we now integrate fossils in these types of analysis. So this is again a study that we're currently working on and has not been published yet. But the process is, again, we start with a single species in one rate category. We have speciation events. We can have then fossilization events that are shown by these dots. And then we have also rate shift events or state change events and we have observed character states both for excuse me, for the tip states, for the extant ones, and for the extinct species that we have. The example that we have been looking at here, or first looking at how that model is actually derived. Basically, to calculate the probabilities, we're not really changing anything about our probability calculation, because the examples that we have been looking at are remaining the same. The only thing that we're saying that in our observed lineages, we don't see a fossilization event. So the first scenario, we say it's no speciation, no extinction, no fossilization, no state change. Second one, we're saying there was a speciation event, but then the left branch went extinct, or you didn't even find a fossil from it, so nothing really has happened there. The third scenario is the same type of thing, just for the right side. And the last example is if you have a state change. And for the extinction probabilities, it's the same thing as before, where either the extinction probability in the short time interval it actually went extinct in lineage, or that no event happened, so no speciation, extinction, fossilization, or state change, and then subsequently it went extinct, or speciation and then the two lineages went extinct, or there was the rate change. So not really a big change from what we had previously by integrating now fossils as well. And the nice example that we have been working on here is fossil crocodilians with the extant ones, and looking at different ecological states. So we have three different ecological states. They are terrestrial, semi-aquatic, and marine. We have this phylogeny with the extinct and extant fossils. And we see that, for example, all the extant crocodiles are semi-aquatic. We don't have any currently extant one that are terrestrial or marine. What we have from the fossil record, we know a lot of them, they were marine or terrestrial. And by including that into our phylogenies, we are getting a much better and much more interesting picture now, where we can estimate that the speciation rate for the marine ones was actually much faster than the semi-aquatic one, which you might not have expected if you just see that today all crocodiles are living in a semi-aquatic habitat. So we can also see that it's not only the speciation rate that it's much faster for the marine crocodilians, but it's also the fossilization rate and the net diversification rate that is much faster. Why in the end all the marine crocodilian went extinct can't really be seen from this analysis, but it's mostly driven by the state changes that most of the marine crocodilians then moved back to a semi-aquatic environment or habitat. Okay, so this was a big overview of these different types of diversification rate pattern analysis that I've been working on with quite a larger set of collaborators, and this here's the just a short overview of my main collaborators, which are Fabian, Andrew, Will, John, Andy, Mike, Ryan, Bruce, Isabel, Daniela, and Alan, mostly in Europe and North America. Thank you for listening.
All right, thank you very much. That was a really interesting and action-packed talk. So if you have any questions, go ahead and tweet or type something into live chat. So can you just say a little bit more about the conditioning that you are doing in order to sample the hidden things that allows your algorithm to be so fast? So what is exactly the conditional distribution that you're sampling from?
Which algorithm are you talking about?
So you're sampling, like you're doing ancestral state mapping in order to...
Right. So basically what we are doing here is for making our algorithm much faster is we are doing similar to the standard Felsenstein spooning algorithm. We're calculating the probability starting at the tips, and we're going to the roots, and we are calculating what these probabilities are going backwards in time. And I think I had the slide then. Once we did that, so once we are at the root state, we can calculate the marginal probability that we are at the root. and just draw a root state in the stochastic character mapping from that distribution. And then we are discretizing in small time slices forwards in time towards the tips, new time points when we want to draw new states. And we're solving the same differential equation, or the equations that we solved backwards in time. Now we're solving them forwards in time towards the tip state, and calculate sort of if you have the conditional likelihood coming from the tips and the conditional likelihood coming from the last observed state going forward. So this is basically the Viterbi algorithm to calculate what probability there is at this hidden unobserved state. And if you have them coming from both sides, you can calculate what these probabilities are and just draw the state according to them.
But what I'm not following, and I'm sorry, but the things that we're sampling are the rate, are like what the rates are at each location on the tree.
Yes.
How do you know a priori what those rates are at the tips? And I thought, in order to do what you've described it, I would think that you would need to know what they are at the tips.
At the tips, we don't know what these rates are. So we integrate over these rates at the tips. We're just saying that at the tips, they can have been in any rate category, similar to when we look at molecular data, when we would say this site for this species is unobserved. So we're saying the conditional likelihood starts with 1 for each possible character. And then at a given point, like here, we see we want to calculate the probability of what is at this black line that is tipwards, right? And we get the conditional likelihoods that are coming from the tips, and they don't need to be conditioned on a given state.
Okay.
And then given those conditional likelihoods that we can calculate coming from the tips, we only need to multiply it with the conditional likelihood coming from the other direction, coming from the direction of the root. Okay,
so we calculate sort of lots of marginals, and then we go back and sample from those.
Exactly. So we start by calculating the marginals, and then we go in tiny time steps or slices. We go through the tree to actually paint the tree if there was a rate change or not in this small time interval. So basically, we do this stochastic character mapping or simulating to do that. And it's in that sense, it could be similar if you think about any other type of stochastic character mapping or ancestral state estimations.
That's totally cool. I love how you're sort of bootstrapping yourself, because you don't have any data to begin with, but you can go around and calculate these marginals and then sample. That's cool.
Yeah. So the data really comes in from the speciation and extinction events. You don't really need the states at the tips. Yeah.
And the regression modeling is pretty cool. So can one just write down that type of regression model in the Rev language, and then how does that actually get encoded?
Yes. So this is really just written in exactly that way in the Rev language. You're just saying that for every time interval, you have a speciation rate and an extinction rate, and you're calculating the speciation rate for that time interval by this regression function by saying you have your background rate, or the intercept, plus, or in any type you want to have it, like plus the regression slope and the predictor variable at the time interval, and then plus adding an error term. So if you would leave out the error term, you would have it directly like a one-to-one correspondence. And in that way, since you write it in RevBayes in just that Rev language, in that way, you could change that regression function in any way you probably think could fit better. So I think people have not really started exploring that much, and this is where I think it could be very exciting to see if these regression functions should be autocorrelated or should be not correlated, how this regression changes, if it's more the change in the predictor variable or the absolute value. So yeah.
Cool. Can we go to the Chromo SSC model?
Sure. I think I need to jump forwards here a little bit. Here's our Chromo model. Okay.
Okay, I mean, I didn't actually know these words before I had looked them up as you were talking, but so this is like change that's happening on a branch, but without a diversification is anagenetic?
Yes.
Phylogenetic means it's happening at.
Right. So this is something that is like in biogeography, you could say there's range expansion that has happened without a speciation event, but you could also have a dispersal event, and a dispersal event could lead to a speciation event at the same time that is then cladogenetic. So these ideas in biogeographic modeling have been used before, but they have not been used in much in other types of modeling. So by just applying the same type of framework that we're doing, looking now more at where these changes have happened and trying to get all these ideas back together. Do state changes in general rather appear anagenetically, so have no impact directly or consequence on the speciation, or are they generally leading also to speciation events?
Yeah, I mean, so you have to take some prior about like what is the I mean, I don't know if you express it as a probability that a diversification happens on an edge versus at a node, or if it's a rate sort of thing.
Yes, you can specify that either as a probability that a change is cladogenetic or anagenetic, or as we have also done it, is you have two different rates. One is the anagenetic rate and one is the cladogenetic rate. But in the end, I mean, you can parameterize it in completely different ways.
One thing I'm curious about is, I mean, if I understand correctly, all of your inferential stuff should do absolutely the right thing, right up toward close to the present. Is that correct? Or are there some sort of edge effects that have to do with just weirdness having to do with recent sampling or something like that? Or maybe I should ask, what are the sampling assumptions under which your models do the right thing all the way towards the present?
All the right thing towards the present.
I mean, it's easy to come up with bad models that don't take sampling into account and then they get distorted by your sampling procedure that happens towards the tips.
Yes, yeah. I left that out for the talk today and what we have been working on for taking incomplete taxon sampling into account. So for most of these models, what we have is just saying that every species either has the same probability of being included, because that is mathematically the simplest model. Or what can be done also is saying that given that you are in a specific rate category or have a given character state, you have a given probability of being sampled. That can be done. We have for the simpler models that are more the global models, like where diversification rates only change over time. We have also worked on more models where you say, where you have additional information of how many species are missing in a given clade. And what we're doing there is you're integrating over all the possible speciation times in that clade to get more information.
Cool.
But so I think that is also more research in that direction will be needed for looking into if you have that prior information and these more complex models, how we can actually, for example, simulate even under these processes alone to say that we don't have even taxon sampling. And it definitely can give us quite different results if we have violated model assumptions for our taxon sampling.
Cool. And just one last question. I mean, maybe it's totally standard in the field, but I was sort of surprised to hear you say like phrase speciation, increased speciation rate as like increased evolutionary success. And I guess in a sense that makes sense because obviously the species is thriving if it's kicking off new species, but the opposite doesn't necessarily obviously seem to be the case, right? Like maybe there's just a successful species and it's just successful and it doesn't need to speciate further. Is this just a language thing?
Yes, that's probably mostly a language thing because here I was not considering a species to be successful if it speciates a lot. It's yeah, I think that is a completely different point of view.
I thought you said evolutionary advantage.
I was looking into yes, the evolutionary disadvantage for, I think that was here the example. Looking at the evening primroses, looking at self-compatibility and incompatibility has the advantage or disadvantage. And we are rather looking here not at a single species, and I think this is where the language and the perspectives change, because we're looking at the entire group. So all the lineages like the Clarkia that are self-compatible, and they are in the evolutionary disadvantage because they have negative net diversification rates.
Cool.
So I think what you're saying, what could be very interesting there is looking into what for some of these species is the chance of going extinct. Because even if you have a negative extinction rate, the chance of going extinct really depends also on absolute rates of extinction. But if you see also in this, in our estimates here, that the self-compatible states have by far the highest extinction rates.
Right. Yes. Okay. That makes perfect sense.
Yep.
Okay. Well, thank you very much. I appreciate your dedication and like trying to like make this work after you got sick. And just in a few days, we're gonna have Benjamin Good.
Okay. That sounds great. Thanks a lot.